Hello and welcome to Math for Honors with Mr. Weiler. Today what we're going to be doing is starting off on I think a new project where I start to go over major errors that have occurred on assessments through video rather than taking up classroom time for it. Research has often shown that it's probably some of the least productive class time out there because students are thinking more just about what the result on the test was, and they're not really so much paying attention to the errors that were made on the test. So we're going to kind of test that theory and maybe make some videos in the future and highlight errors on tests or assessments or quizzes. In this particular video, what I'm going to be doing is I'm going to be going through the entire Quiz 3 Marking Period 2, which concentrated on one problem that was all about implicit derivatives and one problem that was all about differentiability. These are both really challenging topics. Some students nailed the quiz beautifully, some students really struggled on it. I don't make any judgment call on people that struggle on this. This is tough. Even though we did two problems very, very similar to them on Monday, these are tough, tough concepts. So let's take a look at it. All right, the first question was an implicit derivative question. It gave us a curve defined by this equation. Now, one of the things that's really tricky about this kind of problem is that students really, I think, struggle with the idea that if I give you an equation, whether it's in an explicit form or an implicit form like this one, it defines a set of points in the plane. It defines some set of points y versus x. And we can still talk about what the slope of the tangent line is at any one of the points that lies on the curve, right? Now again, it's very important to understand. It's this rule right here, that completely and utterly dictates the points that lie on this curve. If a little point over here, x comma y, makes that equation true, then it's on the curve. And if it doesn't make it true, it's not. Anyway, you don't really need to understand any of that in order to do letter A, where it says, show that dy dx equals blah. All right, so let's go through the procedure for finding an implicit derivative again. Remember, we always start that off by taking the derivative of both sides of the equation. Some students are still a little bit confused about this notation, and I get it. You do not want to have dy dx equals in this problem. You want to take the derivative of both sides, and you don't want to have a y sitting here or here, because that implies that you're multiplying dy dx by this quantity, and you certainly aren't. This is what's known as the derivative operator. It says take the derivative of what's inside. Now, the derivative operator distributes over addition and subtraction, which is really nice. It doesn't over division and multiplication. That's why we have the product rule and the quotient rule. Sorry, I have to continually talk. The derivative of a constant is, of course, 0, and I believe almost everybody in the class has that, so that's not a problem. Now, here comes the problem with implicit derivatives, and I know some people are still confused about this. The idea here is, yet again, y is a function of x. So if we have something like the derivative of y to the fourth with respect to x, we have to look at that as the chain rule, i.e. we forget about the y and we say that the derivative of something to the fourth is 4 times that thing to the third. But then we have to go on and multiply by the derivative of what's inside. Now the derivative of what's inside is literally what we are trying to solve for. It is dy dx. It is y prime, right? So, if you don't understand that from the concept of the chain rule, and I understand I was gone on the chain rule, but still, at some point, you have to process the form of the chain rule and the idea of it, then at least do this. If it has a y in it, take the derivative the way you always would, and then multiply by dy dx or y prime. So here we go. The first thing we have to do is take the derivative of y squared divided by x, and of course we need to do that with a quotient rule. A few people expressed x that as times x to the minus 1. Most people were not successful when they tried that, although it would work. Anyway, here goes the quotient rule. The quotient rule says take the derivative of the numerator. Well, the derivative of y squared is 2 times y, but then we have to multiply by y prime. That's the deal over here, right? But then we have to multiply by the denominator, which is x, minus. The derivative of the denominator, well, that's just normal because it has an x in it. So that's derivative is 1 times the numerator, which is y squared. And then we have to divide that all by the denominator squared, minus. This is where a lot of people botched it up. Now, if I said, what's the derivative of 2x, almost everybody in class would say 2. So the derivative of 2y is also 2, but again, we have to multiply by y prime. And all of that is equal to 0. Now, at this point, all of the calculus is over. It's all about the algebra involved in finding this. So many people got to this stage and it fell apart not due to the calculus, but due to the algebra. Now ultimately what's throwing me off in this problem is that I have a fraction. There's an x squared. Well, last year what we learned is an effective approach to getting rid of that is to simply multiply both sides of the equation by that denominator, okay? Now remember, it's going to distribute. It's going to distribute over this, and it's going to distribute to this. When it distributes to this, simply these two cancel, and we're just left with 2y, y prime x, minus y squared, because all of that is one term. It's all being divided by x squared, so when we multiply by x squared, those two operations cancel. On the other hand, we do have to multiply this guy by x squared because of the distributive property of multiplication, I guess, over subtraction. Sorry about that. All right, well now this makes it a lot easier, because what I'm now going to do up here is I'm going to factor a y prime out of the two terms that have it, and that's 2 times y times x minus, it's also over here, minus 2x squared. And then I'm going to take this term, which doesn't involve a y prime, and I'm going to put it on the other side. And then I'm going to divide both sides by this quantity, right? And by now, my hand is killing me. I don't know why, probably because I haven't done a video for a little while. And I have the desired result. In fact, I'll even flip-flop that x and y just to make it look exactly the same, but of course I can do that because multiplication is commutative. All right, so again, a lot of key steps here, a lot of key mistakes that people made along the way. Some of them were algebraic, some of them were in the pure concept of what it means to do an implicit derivative. Please make sure that you understand this basic operation. And I know it's tough. I know it's difficult because it involves the chain rule, it involves implicit functions. Let's now go on, though, and apply this. So pause the video now before I scrub out the text. All right, scrubbing. Sorry, I'm kind of in a rush to get this done before second period. Okay, letter B. There is a single point on this curve where the tangent line is vertical. All right, let's envision something like that. You know what I could envision is like a parabola that's maybe like tilted like this. Do you know what I mean? Because then there might be like this one point where if we drew in the tangent line, it would be vertical. We're supposed to find this point algebraically. All right. Now, again, let's talk about vertical lines. The key with vertical lines is that they have a run that's equal to 0. That's really what makes a line vertical. Yeah, I'm good. So the key is when we look at a slope and we think of slope as rise divided by run, then ultimately if we have a vertical line, the run must be equal to 0. And most people did that just fine. It was very, very rare that people didn't start with that, and that's wonderful. Now the question is, what do I do with this? You know, if I get something just like x equals 5, awesome, then x is 5, right? I might not know what to do then, but it's great. What in the world do I do with this? Well, let's solve it. Now, I'll be honest, I gave a lot of credit for incomplete solutions on here. Listen to this carefully. I gave a lot of credit for incomplete solutions on here. So I want to show you the complete way to do it, the complete way. A lot of people just put the negative 2x on the, a lot of people put this on the other side, and then divided by 2x to get y all by itself. And I gave full credit for that. But I do want to show you the proper way to do it. The proper way to do it is to use the zero product law. All right. I want you to think about the factoring. Okay. Now what that means is that either 2x is equal to 0, and this is very important, or, not and, y minus x is equal to 0. Now in this case, we get the solution, x equals 0, and we should really look at that guy. We should. And then in this case, we get the solution y equals x. Now what do we do with both of these? We still haven't found the magical point. We haven't found this thing. How do we take this condition and do something with it? Well, a lot of people made a really critical error, and I understand this. I made this error so many times, even by the time I was in college going through engineering, I still would do this. A lot of people substituted this back into here. Whenever you substitute an equation into itself, it's great. Whenever you substitute an equation into yourself, what eventually has happened is you'll get a tautology. You'll get something like 0 equals 0, 5 equals 5, 3 equals 3, which does nothing for you. It's truth, but it does nothing for you. What we need to do is take this condition, or these conditions, I apologize, which are all about the slope, and substitute them back into the curve that dictates the points. You see, if we're looking for a point on the curve that satisfies a slope condition, then eventually we have to use the equation that dictates the points that live on the curve. Isn't that cool? So I'm going to take both of these. Let me now switch back to blue because I'm tired of the red. Let me take x equals 0 and plug it in. Well, what do I get? Y squared divided by 0 minus 2 times y equals negative 1. Well, this is impossible. I'm not going to say does not exist. There's just, I can say no solutions, that's fine. And now let me do with the y equals x contingency. Well, if I put that one in, I get this. Then I get, be careful here. I had some people tell me that x minus 2x was negative 3x. That's, to put it mildly, a little weird. I get x equals 1. Now, don't make your life hard. Don't do this. Do this. Ooh. Don't get me wrong. You put it up there, you'll also get y equals 1. But why take the pain? You know what I mean? So the point 1, 1 lies on the curve and satisfies this slope condition. Oh, and look at how pretty that screen is. All right, pause the video now and copy down anything you need to. Okay, here scrubs the text. How much time do I have? I still have enough time. I can get it done. Assuming something terrible doesn't happen. Okay, number 2. Let's play with the piecewise function. Let's make a piecewise function differentiable at its cutoff point. All right, we have these two curves. They're coming together. They're actually two different parabolas. One's concave down, because I can tell that because of the negative. One's concave up because I can tell that this one has a coefficient of 1 on the x, but whatever. We'll see that in the graph. I'm going to scrub this right away. But anyway, we want to make this function differentiable at x equals 2. Now remember, this is really all about two things. We have to make sure that it's continuous at x equals 2. And we have to make sure that there are no corners at x equals 2. Now I'm cutting no corners here. Do you notice what I just wrote down? This is really important. A lot of people are missing this fact, and I'm not sure how to get you to understand it other than really hammering it home right here, all right? I'm not trying to do this at x. I'm trying to do this at x equals 2. There's only one number I care about in this problem, and that's x equals 2. Not one number, but one place. So now how do we make a piecewise function continuous at the cutoff point? Well, the easiest way to do it is to set the output of one of the formulas equal to the output of the other formula when x is 2. I'm not going to wait around to plug this in. I'm going to plug it in right now. Now, a lot of students felt the need to multiply this out. I totally understand that. But if you don't see an obvious advantage to doing something that requires time, don't do it. Okay? Don't do it. So in other words, it took me no time to say that 2 squared was 4. But it's going to take me a while to multiply that out, even if I can do it in my head. So let's move over to no corners. All right. Now for no corners, that means that the two slopes must be equal at x equals 2. Right? This is the two y's are equal. Here the two slopes must be equal. But to be able to figure out the slopes, I have to be able to take the derivative. And here a lot of people made mistakes, so I want to take a look at this closely. All right. Now remember, A and H are constants. So I would encourage you, anytime that there's sort of a constant in a problem that isn't specified, if it confuses you at all, what I want you to do is on the side, I want you to make up a different problem and throw constants in. Okay? So I'd like to keep track of this and this. Now I want you to think about it. If I took the derivative of 5 minus x squared, the derivative of 5 would be 0, and the derivative of x squared would be negative 2x. Likewise, if I take the derivative of a, I'm going to get 0, and the derivative of x squared will be 2x, right? So I'm going to get a derivative of negative 2x. Now let's take a look at this one. I'm obviously using the chain rule. The derivative of something squared will be 2 times that thing to the first. But then I have to multiply by the derivative of the inner function. But what is the derivative of x minus 3? Well, it's the slope of the linear function x minus 3, but that's just 1, right? So that's just 2 times x minus 3. And likewise down here, this is just going to be 2 times x minus h. All right. The key now is I need to set negative 2x equals 2 times x minus h. Those two slopes must again be equal at the cutoff point, otherwise we get a corner. That's what makes a corner, is the fact that the slope from one side isn't equal to the slope from the other side. Think about the absolute value, right? Slope of 1, immediately transitioning to a slope of negative 1. They don't meet at x equals 0. Anyway, this is where a lot of people failed to plug the x equals 2 in, and it really just threw them off to no end. But look at what happens when I throw in the x equals 2. Now many times at this point you still have the two constants, in which case you have to solve a system. One more time. At this stage, many times you still have the two constants, in which case you still have to solve a system. But here you are solving a system, it's just an easier one, right? It's just an easier one. I'm solving this, by the way that I think most people will solve it. Right, I get h equals 4, and the beautiful thing now is I can simply substitute it into here, right? Sorry, it just doesn't seem to make any sense for me to talk while I'm just doing arithmetic. And there it is. We will work on and off this year, especially when we do modeling, on making piecewise functions connect at their cutoff points and connect smoothly at their cutoff points. It's a really important thing in design, things like roller coasters. I know I've cited that in class before. But it is tricky. It almost always involves a system. Sometimes by the time you're setting the corners equal, setting the two slopes equal, one of the constants that you're looking for has gone away, but sometimes it hasn't, in which case you have to solve a system, right? But that's a system typically of just two equations with two unknowns. All right, anyway, pause the video now if you need to, and then copy down anything you have to before I clear out the text. All right, the last thing I wanted to do in this video was to remind you how to use your calculators to graph a piecewise function. So this is kind of cool. Let's actually take a look at what this looks like now. Remember, what did we have? For some reason, I've just forgotten it from a second ago. A was equal to 8, so we had the function 8 minus x squared when x was less than 2, and h was equal to 4. So we had x minus 4 squared for x greater than or equal to 2. So let's do a little bit of magic on the TI-84 Plus. Are you ready? All right. Hello, TI-84 Plus. So what we're going to do is we're going to put this in, all right? I'm going to review, and for people who are watching this that aren't in my class, might be kind of a neat way to see how to graph a piecewise function on a TI-84. So let's go into Y1. All right. Now here's where the weirdness starts. We're going to put the first formula in parentheses, all right? So I'm going to put in parentheses 8 minus x squared. Now I'm going to close the parentheses. Now I'm going to put another parentheses. I'm literally going to multiply this formula by something. what I'm going to do is I'm going to put in that x less than 2. So I'm going to put in x. Now, to get the less than symbol, you have to go into what's called the test menu. That's right above the math button. So I'm going to go into the test menu, and there's all my tests: equals, not equals, greater than, less than, greater than or equal, etc. So I'm going to go down to less than. I'm going to grab that, and I'm going to put 2. I'm going to put in parentheses. All right, just want to make sure that formula is all good. Okay. Now, I think what I'm going to do is I'm going to change this up a little bit from what I did in class. What I did in class is I then added the next formula. I added the next formula on. I'm going to actually put the next one, into y2. Let's see what happens there. What I like about that is then when we have the transition between the two, the graph will change colors, okay? So in y2, what I'm going to do is I'm going to put in a parentheses, all right? Then I'm going to put in another parentheses. I know, it seems a little weird, but I'm going to put in x minus 4 parentheses squared parentheses. You really don't need that extra set, but I'm kind of emphasizing that you put the full function inside of a set of parentheses. Then another parentheses. Now I'm going to put in that x greater than or equal to 2. So x, go back into that test menu. There's my greater than or equal to. Let me grab that. All right, put in 2 and parentheses. All right. I worked out the perfect window earlier, so let's go into our window. Going into that, let's see, what do I have? I got x min is -5. My x max I figured out is a good one in 10. And my y min I'm going to put in as -10, so the standard. And then my y max as +10. So standard window on y. A little bit different on x, because I really want to sort of concentrate on that area around x equals 2. All right, check it. Looks good. Let's hit graph. All right. Is that neat or what? You know, if I gave that graph on a test, and I said, is this a quadratic or is it a cubic? I would hope every one of my students would say a cubic. And yet what this is a spliced quadratic pair, right? It's a quadratic pair which right there at that cutoff is just meeting up with the same y values and exactly the same slopes. Exactly the same slopes. One of the things I find fascinating about it is that the point of cutoff is clearly an inflection point, right? Because we're transitioning from a concave down parabola to a concave up parabola. But watch this, right? If you took the first derivatives, right, you'd get -2x, and then you'd get 2 times x minus 4. And if you took the second derivatives, what you'd get is you'd get -2, and you would get +2, right? Now think about this for a second. This is a wonderful example of a function that has an inflection point at a location where the second derivative doesn't even exist, because coming from one side it's -2, and coming from the other side it's +2, right? So we're getting an inflection point, a beautiful one, a beautiful transition from a concave down portion of a graph to a concave up portion of a graph, but not at a location where the second derivative is equal to 0, but actually at a location where the second derivative doesn't even exist, because coming from the two sides, it's different. All right. Well, enough of that. Let me put away the TI-84 Plus. All right. I'm going to clear out the text, and we're going to end this quiz review. All right. Well, thank you for joining me for going over this quiz. I hope that even if you were just looking for some problems on differentiability and implicit derivatives, this might have helped. But for my students, remember, you can use this to work on that sort of additional optional quiz to see if you've mastered these topics any better. All right. Well, thank you for joining me, and we'll see you next time. This has been Kirk Weiler for Arlington High School. Remember, keep thinking and keep solving problems.